Today we want to talk about Chapter 6, the behavior of proteins or enzymes. And we will cover the following topics: enzyme kinetics versus thermodynamics, rate of enzyme-catalyzed reactions, enzyme-substrate binding, the Michaelis-Menten approach to enzyme kinetics, example of enzyme-catalyzed reaction, and enzyme inhibition. Now, as it's known, enzymes perform many functions. One of the most important functions for enzyme is called catalysis, in which enzymes act as biological catalysts. They are, as we studied, globular proteins have various functions. One of them, if it is an enzyme, then it will act as a biological catalyst. It will speed up the reaction by a high factor. Now, we can say that all enzymes are proteins except for self-splicing RNA. The so-called ribosomes is the only exception. These are not proteins. So enzymes increase the rate of reaction by a factor of up to 10 to the 20 over an uncatalyzed reaction. The non-enzymatic catalyst enhance the rate of a reaction by factors of 100 to 10,000. طبعا enzymes are high specific to the extent to which they can distinguish stereoisomers. تخيلوا enzymes ممكن يميزوا بين مثلا L و D isomers بين R و S وهكذا. They are very, very specific in the reaction they catalyze. In many cases, the action of enzymes are fine-tuned by regulatory processes, as we will see. سكروا اللي عندكم، سكروا الميكروفون اللي عندكم. If you now we want to talk about some concepts in thermodynamics. The standard free energy change, which is the difference between energies of reactants and products under standard conditions. Enzymes can speed up reaction, but they will not change the equilibrium constant or the free energy change. Now, reaction rate depends on its activation energy, which is the energy input required to initiate a reaction. Imagine a reaction between glucose and oxygen to produce carbon dioxide and water. It requires a number of enzymatic catalysts because you need energy to initiate it. If you put glucose by itself, it's exposed to oxygen all the time, but it is very stable. So what you need something called activation energy, which is the energy input required to initiate a reaction. So you must initiate the reaction. As the gas itself, you must ignite the gas in order for it to give you a fire. Now, delta G naught for an uncatalyzed reaction is higher than that for a catalyzed reaction. Now, this is called the standard free energy change. It is the difference between energy of products minus energy of reactants under standard conditions. Now, there is something called the transition state. And the transition state, if we, you see, this is activation energy, and its relationship to the free energy change of a reaction can be shown schematically by this. If you plot free energy versus progress of reaction, you see here, you start with the reactant, and then you need this minimum energy called the free energy of activation to initiate reaction in order to reach into the transition state. And then it goes down all the way to give products. So the difference between energy of reactants and the transition state is called free energy of activation. And the difference between energy of products and energy of reactants is called the free energy change, or delta G naught. This is carried out under standard condition. For example, if you have a gas, then it's atmosphere. If you have liquid or solution, it is 1 molar. If it is مثلا metal, must be in its elemental state, and so on. This is the meaning of delta G naught, or the standard states. So again, intermediate stage in a reaction in which old bonds break and the new bonds are formed. At this place here, old bonds are broken and new bonds are formed. In the plot of the energies for a spontaneous reaction, transition state lies at the maximum of the curve. Then always at the top of the curve, you can identify the transition state, connecting the reactants and products. Now, delta G naught can be the amount of free energy required to bring the reactants to the transition state. So this is the difficult stage, to bring the reactants to the transition state, and this will go down all the way, as if you are pushing a rock from down up the hill. You need energy. Then after it is here, you can, by a little effort, push it a little, and it will go all down all the way to the most stable state, the one with the lowest energy. Okay. So delta G naught of a reaction remains unchanged when a catalyst is added, but the activation energy E is lowered. Here, again, this is a comparison of free energy of activation profile for catalyzed. This is catalyzed, and this is uncatalyzed reaction. لاحظوا how the free energy of activation of the catalyzed reaction is much less than that of uncatalyzed. So what did the catalyst do? It lowered. You see this as with the one we saw it before here. So when you add catalyst here, this activation energy is lowered. وبالتالي the speed for a reactant to reach product is increased. So more reactants are converted to product fast. And the concentration of the transition state increases. In order to understand more about this, let's consider the following reaction. The decomposition of hydrogen peroxide into water plus oxygen. Notice that this reaction can occur by itself, but it needs several hours in order for it to finish. So what we do is we add an enzyme. This enzyme will lower the activation energy and speed up the reaction. So delta G naught is lowered if the reaction is allowed to proceed on platinum surfaces. This is one way, but is lowered more by enzyme catalyst. Now, if we look at this table here, you see no catalyst, the activation energy is 18 kilocalorie per mole, the rate is 1. If we add a platinum surface, this is a catalyst, the free energy drops into around 12, and the rate increases by this factor. However, if you add an enzyme called catalase, you see the free energy drops into 5.5, from 18 to 5.5, and see the relative rate increase by about 650 million times. So this is a very large effect. This is called catalysis. This is the effect of an enzyme on a reaction. It speeds up the reaction by lowering the activation energy of the reaction they catalyzed. Now, if we look here at biochemical reaction that occur in our body. We see here, if we plot percent of maximum activity versus temperature, we see at the beginning there is an increase in activity with increasing temperature, you see, until we reach here. Now, this temperature, or we can call it increasing the temperature of a reaction mixture, will increase the energy available to the reactants to reach the transition state. And this occurs only to a limited extent. Why? Because after that, increasing the temperature will eventually lead to enzyme denaturation. Since enzyme is a protein, so you remember we said denaturation can be carried out by heat. So at the beginning, there is an increase in activity of the enzyme with increasing temperature until we reach this. We call this is remember the optimum temperature for enzymatic activity. For us, it is around 37 for our body. Okay, this is the optimum temperature in our body. But after that, if you increase the temperature more, then the activity drops due to enzyme denaturation. Now, this is a biochemical connection. You can read it by yourself, in which enzymes can be used as markers for diseases. If you have the time, you can read it by yourself. This is for an enzyme called LDH. This is a heart enzyme which is diagnosed by an increase of LDL from heart muscle. It has 5 forms. 3 of them are heterogeneous and 1 is homogeneous. Notice that this enzyme is a tetramer of 2 types of subunits, M for muscle and H for heart. You remember the quaternary structure of protein? We said this is an example. Tetramer, you see, tetramer. أو بنسميه oligomer. Anyhow, as I said, these different these 3 forms are found in the blood, and the measurement of these are called isozymes, by the way. These 5 forms are called isozymes, which are different enzymes that are found in different tissue but catalyze the same reaction. يعني واحد موجود بالمصل، واحد موجود بالهارت، واحد بالدم, but all of them catalyze the same reaction. This is how enzymes are used as markers for disease. Enzyme catalysis, we are still talking about enzyme catalysis for a reaction taking place at constant temperature and pressure, such as A going to B. Change in free energy is given by the following expression: delta H naught تساوي delta S naught plus T delta S. This is, don't worry about this equation, not required. And also this is not required. This is a relation between the standard free energy change and K equilibrium. Yani if you know the one, you can calculate the other, where R is a gas constant and T is the absolute temperature. Don't worry about this slide. Now, rate of enzyme catalyzed reaction. In a reaction of the form A plus B giving P هنا product, rate of reaction can be expressed in terms of أولا rate of disappearance of A or rate of appearance of product. So rate of disappearance of A can be found by this since it is disappearance, by the way, then it is, we put a negative sign. So here, the negative should be here before, negative delta, yani change in concentration of A divided by change in time. Or rate of disappearance of B, because also B is a reactant, minus delta B divided by delta T, or rate of appearance of P, the product. And here, delta P divided by delta T. Delta means change, 2 brackets concentration in moles per liter, and T is the time. So, again, you can measure the rate of disappearance of reactant or the rate of appearance of products. And then you can say that, okay, the rate equal minus delta A divided by delta T, or minus change in B على change in time, or change in product divided by change in delta T. Notice here, this is positive, which means it is a rate of appearance of product. This negative refers to the rate of disappearance of reactant A or B. So we can then determine conclude that rate is directly proportional to the concentration of A raised to F times concentration of B raised to G. Or if we convert this proportionality into equality, then we must put a constant. This constant is called K, the rate constant. Then K, proportionality constant, also called the rate constant. Now, what are F and G? These are small whole numbers that are experimentally determined, and they are known as the order of the reaction with respect to A, F, and with respect to B, G. These are experimentally determined value. Now, the overall order of reaction is the sum total of all exponents. So, in this case, we will examine 3 orders of the reaction. First, second, and 0. Rate of reaction of A going to P is given by the following. Rate equal K times concentration of A. You see this one here raised to power 1, but usually we do not put 1 because it's understood. So here the reaction is first order with respect to A and first order overall, since we do not have except A. Then first order description of reaction whose rate depends on the first power of the concentration of a single reactant. Whereas if you have this reaction A plus B equal giving C plus D, now whose rate equation is given by the following expression, rate equal K times A to the power 1 times B to the power 1. Again, these ones are not shown really, but here for you to understand that this reaction is first order with respect to A, first order with respect to B, and if we add them together, 1 plus 1, then it is second order overall. And K again is the rate constant. So again, second order description of a reaction whose rate depends on the product of the concentration of 2 reactants. Now these are some examples. Consider the reaction of glycogen with inorganic phosphate Pi, and this occurs in glycogen breakdown. The enzyme is called glycogen phosphorylase reaction. Rate depends on concentration of both reactants. So you can write the rate law in this way. R times concentration of glycogen times concentration of Pi. And so we conclude a reaction is first order with respect to glycogen and with respect to Pi, the phosphate, and second order overall. So if you add 1 plus 1, then it is 2. However, also we have the so-called zero-order reactions. Now, reaction that proceeds at a constant rate, independent of the concentration of reactant. For example, for the reaction A going to B, if you see that the rate equal K times concentration of A to the power 0, and you know this anything to the power 0 is 1, so it's equal K. So here the term concentration of reactant does not show in the rate constant, so we say no, the rate is independent of the concentration of A, which means it is a zero-order reaction. However, the rate might depend on the presence of catalyst. So enzyme-catalyzed reactions exhibit zero-order kinetics when the reactant concentrations are so high that the enzyme is completely saturated with reactant molecules. And we will see this as we go. We will see this as we go. So, so here we talked about 3 types of order of reaction: first order, second order, and zero order. Now, enzyme substrate binding. Now, the first step, in order for a reaction, for an enzyme to catalyze a reaction, the enzyme must bind the substrate. The first step always binding the substrate to the enzyme. So here is the substrate, S is the reactant, and it binds to a portion of the enzyme surface called the active site. This binding is via non-covalent forces. The one we talked about previously, remember, hydrophobic, electrostatic, and hydrogen bonding. All these are non-covalent, and at which the reaction takes place. So there is a small portion on the surface of the enzyme to which the substrate binds, and then reaction occurs. This binding is through non-covalent forces, like I said, and van der Waals. Then first step is binding of substrate to the enzyme. If the substrate does not bind the enzyme, then it will not be converted into product. Very simple, you see. If it is not binds, then no reaction will take place. Now, there are 2 models for binding the substrate to the enzyme. Then enzyme substrate binding models, lock and key model. Here, substrate binds to that portion of the enzyme with a complementary shape. Let me show you the picture, and you will understand it more. Here you have your enzyme, and this is the active site, and this is your substrate. In the lock and key model, the shape of the substrate, if we look here, and the conformation of the active site are complementary to one another, متممين لبعضهم البعض. So that this is the enzyme substrate complex formed. This is called lock and key model. This is rather a rigid model and not common. Now the second model, called induced fit model, binding of the substrate induces a change in the conformation of the enzyme that results in a complementary fit. The binding site has a different 3-dimensional shape before the substrate is bound. So if we look at the picture here, you see in the induced fit model, the enzyme itself, the active site is not complementary to the substrate, but the enzyme itself undergoes a conformational change upon binding the enzyme. upon binding upon the substrate. كمان مرة, the enzyme itself undergoes a conformational change upon binding the substrate. Now the shape of the active site now becomes complementary to the shape of the substrate when only after the substrate binds to the enzyme. Then before that, you see, there is no complementarity, but once the substrate approaches and it is about to bind, the enzyme undergoes this conformational change in order to fit the substrate. This induced fit model is rather common and it is more flexible. This model is very common and more flexible model. And many reactions, any enzyme catalyzed reaction take this model through its action. Now enzyme and substrate must bind, as we said, in order to form the enzyme-substrate complex, for which attraction must exist between enzyme and substrate. So E plus S to form ES, enzyme-substrate complex. Now causes the ES complex to be lower on an energy diagram than the E plus S at the start. So at the beginning, if we look at the free energy of activation profile of an enzyme substrate complex, you see at the beginning, E plus S here, enzyme substrate. Once they form the enzyme substrate complex, this enzyme substrate complex has a lower energy than the starting reactant, اللي هم E plus S. So at the beginning, the ES complex has a lower energy than at the start. Then bound ES must attain the conformation of the transition state. So this bound then will take the shape of the enzyme transition state complex EX, and this is the one in which the enzyme lowers its activation. It is the enzyme transition state complex, not the enzyme substrate complex, because this has a lower energy already. But this is the one. So with two things, with the proximity, with the proper proximity and proper orientation of the substrate, speed up the reaction. So the enzyme with proper orientation and close enough, it will lower the activation energy and go down all the way to generate the product. Notice here that the enzyme, as it entered, it emerged without any change. So the enzyme enter and comes out unchanged, and this is a characteristic of any catalyst. A catalyst usually enters and comes out unchanged. Each enzyme has its own unique mode of catalysis, which is not surprising in view of enzymes' great specificity. All the enzymes are very specific in the reaction they catalyze. So again, once the enzyme substrate complex is formed, then products start to emerge, and catalysis begins, and the products start to form, as you can see here, product form, and then after a while, product released. So here you can see the formation of product from substrate bound to the enzyme, followed by release of the product. Two enzymes, chymotrypsin and aspartate transcarbamylase, are good examples of these general principles. And we will talk about two enzymes and compare between them later on because they follow these general principles. The Michaelis-Menten approach to enzyme kinetics. Now, a useful model for the kinetics of enzyme-catalyzed reaction was devised by two scientists, Leonor Michaelis and Maud Menten. This is in 1913. And it is still the basic model for many enzymes and is widely used, even though it undergone many modifications. A very simple reaction might be the conversion of a single substrate to a single product. Yani it's going to be, and the mechanism for an enzyme catalyzed reaction can be summarized by this. This is the mechanism. Then, if you have a single substrate converted to single product by an enzyme, then you can write this stoichiometric, then you can write this enzyme catalyzed reaction in this way. E plus S, here two arrows, and we have two K1 and K minus 1 to form ES, and then this ES will generate the product, and we have K2. All these, K1 is the rate constant for the formation of ES from the enzyme and the substrate, whereas K inverse 1 rate constant for the dissociation of the ES complex. Then K minus 1 for the dissociation of the ES, yani from right to left, whereas K1 from left to right. However, K2, as you can see here, rate constant for the conversion of ES complex to product P and the release of P from the enzyme. Note here that the assumption that the product is not converted to substrate to any appreciable extent. Then here in the reaction in this Michaelis-Menten model, خلينا نقول, the product is not converted back to substrate at an appreciable extent. Okay. Now, when in this model, when we plot the initial velocity versus substrate concentration, as you can see here, we will get this hyperbolic type of curve. We call this hyperbolic type of curve, where at the beginning, increasing the substrate concentration increases the velocity. And as you can see, this follows a first order kinetics. يعني rate depends on concentration of substrate. طبعا initial rate or initial velocity V initial or VO, and S is the substrate concentration, and we assume that the concentration of the enzyme is constant. Then after that, at infinite substrate concentration, the reaction would be proceed at maximum velocity. You see here, we have here maximum velocity. And here in this case, no matter how much substrate concentration you add, the velocity is constant. This is a zero order kinetics. Why? Because the rate does not depend on concentration of substrate. And we call this velocity the maximum velocity, Vmax. And it is obtained when the enzyme is fully saturated with the substrate. Now Km, inverse measure of the affinity for, now we want to define something called Km, the Michaelis-Menten constant, and it is a constant which is an inverse measure of the affinity of the enzyme for the substrate, which means that the lower the Km value, the higher the affinity. Rate of formation of the AS is given by the following equation. Now we want to derive the Michaelis-Menten equation, and we will leave this for next time.